It will be presented by Dr. Sadaf Alam. She is from University of Bristol. So she is the Chief Technology Officer for the Isambard Supercomputing Digital Research Infrastructure and the Director of the Strategy and Academia in the Advanced Computing Research Center at the University of Bristol. She is responsible for digital transformation for research computing and data sets and management services. Prior to joining Bristol, she was the CTO at CSCS, that is the Swiss National Supercomputing Center. There, she was the chief architect for 2 generations of systems, including PeaceDent, the flagship supercomputing. She was also technical lead for European Supercomputing Center's project called Phoenix. And then prior to that, she was actually at Oak Ridge National Lab, not very far from Columbus. This is where I got exposed to her in 2004, right, 20 years back. But she has traveled at different places. So she studied computer science at the University of Edinburgh, UK, and she was a founding member of the Swiss Charter of Women in HPC. So she's very active in that direction also. So with this, let's give a big hand to Sadaf. Let's change.
Okay. Close this one and plug it in. Okay, I'll just
Yeah.
You put it on up that one if you want.
Okay.
You want to use it? Okay.
Use this microphone, move
Okay.
around.
Yeah, that will be. I don't have a pocket, so probably like you, I hold it in my hand.
No, there is a clip. You want to put it in.
Yeah, maybe.
Use the clicker.
Clipper is here.
Should I? Is it connected? No. Oh, yes.
I think there should be a port, right? Yeah.
Continue. Shift. Shift on this one. It's usually. Let's skip. Let's just skip it. ISO US. All right. Let's see if it works. Yeah, good. Let's get started. Do I have 1 hour or should I stay?
You go, take time.
Okay, take time. Okay, thanks DK for inviting me to the meeting and thanks for the kind introduction. Thank you all for coming this morning. I think, is it a little bit higher? Okay, that's better. So I started with the thanks. Let's go again. I think I attended the last web page almost 10 years ago. And my photo is also from 10 years ago, most probably from CSCS. So I'm happy to come here and present this very interesting project. But today I will focus on something we do not focus on in high performance computing that much, in the sense of how do we make these systems sustainable, especially for government funded projects, so they are affordable in the long run. So I chose the title for Sustainable Recipes, and I will go through some of the technologies. I will still talk about performance and modular data center, direct liquid cooled computing, which I think supercomputing community knows for a long time, and how to use and target energy efficient compute, and GHG is greenhouse gases emissions. So really paying attention to that. Before I go further, I would say that thanks to DK's team, we are running MWebPitch. Even though this one has a Cray Slingshot interconnect, we have DK's group is running MWebPitch on this phase 1 machine. And the other important thing, which I will not go into that much detail, so what you see here is this screenshot of something called Bristol Center for Supercomputing. It's like a web portal. And the system is also designed to be highly accessible, federated. So pretty much the way you can get on EduROM with your credentials, you should be able to get on this machine like that. So DK's team is on that machine using their Ohio State credentials. So that's kind of something I would add. And the person cartoon character you see up there, it's Isambard. He used to be like most famous engineer of his time. My colleague Simon McIntosh Smith describes him like a Steve Jobs of his time. And so he named the systems after him. So what I'm going to present for the rest of the time is just listed here, mainly 4 main points. So I will start with some introductions. And I know this community is very international, as DK highlighted. So I will talk about some of my international credentials a little bit, but also I will introduce what is Bristol, what do they do, and why working on this project is so exciting, because it's like it's like a startup. I was talking to one of the colleagues, I said, it's really working like a startup. We started with no data center in the team. And then I will go and how Isambard-AI, how we made it sustainable, and the backstory. Why we made it sustainable. I think it's important to know, it's easy to tell why something is, or what something is, but why we got to that point. And then you have probably heard a lot about what AI is doing and machine learning, deep learning is doing, but I will give a little bit AI for science perspective here, what AI is doing for science, and in short, it's a lot and it can do more. I will a little bit say about what we have as early users. So the full system is not being built, like the 5,000 plus GPUs. We have a small 160 GPU system, but already there is so much interest and so much interesting work going on there. I do have some results, including, of course, we are here, so we have to talk about OSU benchmarks a little bit. Not as much as I think your team would like to, but and what's happening next. And before I go further, already in a few months ago in May, International Supercomputing Conference, I was really personally quite surprised because, when you are dug in deeper, doing some work, the system came out as the second greenest system on the Green 500 list. This project, I'll show you a bit of timeline, how this project works. But this could not have been done without full commitment and dedication from not only IT people, but a lot of people behind that, because at the same time the system was built, the data center, the modular data center was built, the concrete was laid out to build that data center. I'll show you some picture. So I sometimes feel like that it is kind of, I don't want to make too many wrong analogies. Everyone was so dedicated and so committed to hit this. We had an end of March deadline earlier this year, that so many people working side by side, like contractors digging up, people doing electrical work, people trying to run LinPack at the same time. I have never seen something like that happening so closely together. So it was really, so for the students starting their career, yeah, we feel like we are working in computing, but this project showed me I have learned so many things about, other things I never knew, and I got to wear a hard hat and high-vis jacket in this project. So it was a true fun and pleasure. So a bit of introductions, and DK covered most of it. I think our field is very interesting and exciting, especially if you are starting this career right now here. I think Webpage is a really good example for that. You get to do a lot of things, and I was quite fortunate to do a lot of things at a lot of different places. But what was the driving theme and what is so important, and I think, DK, you do it a lot in the community, is you form really long-lasting international cooperation through people, through technology, but also through people. And I think that is the really, really key part. And as I was growing up in my career and the other important thing I realized is the role of mentoring that played. And mentor doesn't mean someone has to do something formally. I really value people who, throughout my career, gave just one advice and sometimes more than once, and some people. So I have known so many people, as DK said. We first met 20 years ago, and we are still, in touch in different places and share notes. So it's really important to, formulate. So if you're really starting your career or doing things, just really look out. And if you are like me, lot of gray hair and other thing, try to formally or informally coach and mentor people, because this is a really interesting field. So I don't know how many people know Bristol in sense. So Bristol and University of Bristol is, and if you come and fly to Heathrow, it's not that difficult to get. It's like a 1.5 hour on train. And it has a very rich also technology industry. So the Isambard bridge you see there, that was one of the Isambard invention. So university, compared to many other UK universities, is very new. So it looks old here. And the project Isambard is started by Simon McIntosh Smith almost 10 years ago, looking at ARM. Unlike x86, we take x86 systems for granted, but he was at that time thinking, can we use ARM systems for supercomputing, for mainstream supercomputing? So this is going on for a long time. And after we were funded by a fairly significant amount for building Isambard-AI, now we have formed this Bristol Center of Supercomputing. Officially, in fact, it started 1st of August, just a few months ago. So going on to the main part, what is this sustainability recipe? And how did this all happen? It is still quite amazing, the UK government, how they went about doing certain things. So there are 4 main parts that we really paid attention to in terms of making this thing affordable and sustainable throughout the operation of the thing. And it's also, in my mind, a very responsible thing to do, because AI is computing via GPU. I mean, we hear articles all that about time, how much power it is using, how much water it is using. And some communities are deprived of water just because of these large-scale data centers. So if you do it for using public money for public good, I think this is really, really important to pay attention. So starting from the left, modular data center. Why not brick and mortar data center? Why modular data center? These are built using container technology, so they can be built very quickly. That's okay thing. You can build brick and mortar probably very quick. But the most exciting thing is almost 95, and by some account, 99% of the material is fully recyclable. You can recycle it after, the timeline for which we bought our system is warranted is 10 to 15 years, but should you choose to, because the technology changes, you can really recycle everything. And it's, how do you say, less stress for the environment to build it. ARM and GPU computing, I think, is kind of, in our community, we know that. So this new generation of Grace processor was one of the design choices we had. And of course, GPU for AI computing from NVIDIA is like a no-brainer right now. But together, being on this super chip, there are studies out there, and I have some numbers. There are huge savings for data movement. Then moving to direct liquid compute. So here we use Cray technology, Cray HPE, right now Cray is gone. And so when you use direct liquid computing, you get higher cooling efficiencies. But on top of that, in this system, even the networking is done using direct liquid cooling. And finally, which is this whole greenhouse gas emission. So I just picked up this graph, and there are many other from National Grid website. And then they talk about these scope 1, 2, and 3. I never knew about those things. But when we did put the procurement out, we asked the vendors to provide these emissions. So we are accounting, because you can't improve on something if you can't measure it. And that was the idea. So the idea is to really reduce as much as possible these greenhouse. And I'll talk a little bit how that is being. So really, we are focusing individually and collectively to optimize all of these. So the backstory now, how Isambard was funded. It still surprises me to this day. So exactly a year ago in August, right now, government said we want to build a very fast AI supercomputer because the last government and the prime minister were very keen on making AI safety as a high national priority. And we made this proposal and they came back to us. They said, can you build it? And can you do it very quickly? And I'm not going to say it in a public way, but they were quite, how do I say, generous in terms of funding. And that's why the thing came about. But they put out this announcement together with us, so August and September. And at that time, we were already writing the procurement within less than 1 month. Right about that same time, they announced this UK AI Safety Institute, and they tied the two together. And let's just take like a few steps back. The UK AI Safety Institute idea predated the funding of Isambard, and we should ask why. So before that, there was something called AI Frontier Task Force. And governments, including, I think, US and many others around the world, they realized that, I won't say not by taking the rise of social media and its impact on society earlier on and being always in a reactive mode, with the influence of AI and its usage in the community, they wanted to be like at the forefront of decision making. So this is a little bit of a snippet. If you look up, you can all find it. So they are really trying to very nicely, because they have to sell it to the public, make a case why UK government is going to invest. Because at the same time, they just don't want to block everything. They want to use it sensibly. They want to legislate its usage in the community. And I think same is happening in the US. By some account, maybe UK was a little bit ahead. So, but when they realized they have to do it, they at the same time realized you can't go into a modern fight with a sword. So if you do not invest in the compute at the government level, you have absolutely no chance on fighting, big institutions that are pouring unimaginable amount of money for training. And this is, Isambard-AI by no sense of it. It's really very, very small. You see the numbers, 20,000, 100,000 GPU systems all the time. But it just gives researchers a chance to do something more than they can do with a few hundred powerful GPUs. So that's how it came about, that investment in AI safety, but also that requires the science part of it, and then the investment in compute. So I'll go a little bit quickly because I think I'm probably going a little slower right now. So this is the timeline. This project, I have been, as you know, I've been in the community for a long time in many, many different countries. I never, ever did something that, crazy before. Starting with nothing, and in less than 6 months, we had a small working system, and already in a few months' time. And the project started in this car park. And up until we were writing the procurement and building the system, it was still very much a car park. But the main motivation is down there, this UK AI Safety Summit, where you can still recognize some dignitaries. The Prime Minister in the UK is gone now. Maybe the new one here, who knows how the US elections will go. So we can hope. And then we hired the team in 3 months, just the startup team, and hiring a little bit more, and already people are running there. So this is pretty neat. But the question was how we got up to this point. So Isambard-AI followed almost three other Isambard projects, Isambard 1, 2, and 3. And if you recall, these were about using ARM for supercomputing in a production sense. But Isambard 1 and 2 were hosted by the UK Met Office. And the UK Met Office decided to go with Microsoft Azure for their next procurement. So they no longer have a data center. So that's where the idea of the modular data center came about. what do we do? Now we not only have to build a system, but we also have to build a data center. So we considered a few options, and we could have considered more, but the options considered what can we rent an space from an existing data center. But existing data center spaces, first of all, come very expensive, and these data centers are not designed for very dense compute. So that was not an option. Building a new one with the UK planning permissions, and we can talk offline how that goes, I still do not understand a thing, would have taken forever. So that's why we came about. So what is a modular data center? It's pretty much, as the name suggests, modular and self-contained. So you could bring it in different shapes and forms. You can bring it like complete with everything, power, cooling, everything necessary to run a center, or you can bring in where you can provide a lot on site and come in a pre-built data center. So it's like, someone described this, like a Lego block. And you have quite a bit of flexibility. This is what I saw compared to a brick and mortar data center. You can pretty much tune the zones for directly fit compute, for high density compute as you go quite easily, which it requires a little bit more work on a normal, brick and mortar data center. You can decide which parts you will have more resiliency and redundancy, anything. And because of that flexibility, you can build and commission some of these things in like a few months. And then it can accommodate different type of environment and conditions. So the company I visited that built that modular data center, they were at that same time building next to Isambard, a data center that will go in a war zone for NATO. Just to give you an idea, and that was Isambard is not designed to sustain or with in a war zone scenario. It's quite sustainable. You can get really fine-grained telemetry out of it, and then it's upgradable, refreshable very easily in 10 to 5 years life cycle. The picture you see there, it's like the parking lot where the Isambard is going, and you can see where Isambard-AI phase 1 and phase 2 are, and where Isambard phase 2 is kind of being built. And this is almost 11 months. I didn't update it, but it looks a little bit different on how the thing converted from a car park. And this is a UK car park. So the parking bays are narrower, as you can imagine, compared to a US-based car park. So I think what you see 4 lanes is probably a fewer spaces here. But all of this goes into 4 rows of about 20-some parking spaces. So all Isambard-AI 3, the fastest system in the UK, will be just done here in a less than 2 minutes. It rained a lot. It's UK. But people say it's rained even longer, so it took us a long time. So what you see far there is already Isambard-AI phase 1 going there, and they are digging up for phase 2 here. And that should come later this year. So all the power, utilities, and other things are going in there. It's quite interesting to be on that site. It just makes you quite humble about, sometimes your work, that what you do. So in going in deeper, so we set really in the procurement some optimization target. One is the most obvious one is the PUE. I think Isambard-AI for the most part will go probably 1.06. 05, and in some cases we have looked at it because it's largely using free air cooling. Bristol doesn't get very hot, and I'll have some more data in there. And then on the power sources side, because we are bringing in a lot of power, we can choose all non-fossil fuels. On top of that, the heat coming out of the data center will be used to heat the buildings nearby, and the local, county is building a district circuit, and the heat could even go there. University of Bristol almost 3-4 years ago set a target which they call net zero 2020. When Isambard was going to get funded, there was almost like a dilemma for the university. They say, we really want to do this project, but it will just completely destroy our net zero target because it's going to consume so much power and everything. So in the procurement, we assured the university that we will measure all scope 1, 2, and 3 emissions. So scope 1 emission is pretty much what you generate on site. And there is a small diesel generator kind of thing for UPS and others. So if you completely are out of power, you can pretty much gracefully shut down everything. So it's really virtually nothing. The majority of the emissions is from direct electricity usage. And we say we could count, because it's a national facility, we could account for it on the government book, account sheets. It won't be considered our emissions. And the third one is really the most difficult one to capture. It is about the whole production movement of each and every part, and there you need input from the vendor. For instance, HPE has to kind of tell us, together with NVIDIA, what is the emission for producing each and every individual component. And companies are now, in most cases, in some countries, even legally required to put those things out. So they worked with us, and in the proposal, those values are captured. So they account for about 10% of overall, and this is based for 5 years, the storage. So, and then even the IT will be locally recycled. So the idea is we will not, after 5-6 years, Isambard is decommissioned, HPE assured us that there is a facility in Scotland where all the IT components will go and get recycled. So this is where I think I will talk about where Isambard is being built, but I have a few slides that probably will not be fully appreciated by our NVIDIA colleagues. So this is the National Composite Center. And it's really very neat facilities, very bad. And where they, as the name suggests, they have equipment to research composites. And because of that, because they have literally really giant ovens where they can make full span of aircraft wings. So they use a lot of energy, but it's very bursty. So when they power up an equipment, that's where they can use up to 2 megawatts and even higher. But most of the time, it's very low usage. So they had a car park as part of that. It's outside the city. And after pandemic, the car park usage went down. And when Isambard was location for Isambard was concerned, they say, oh, you can use this bay because we use less than 50% of our capacity normally. So that's where Isambard goes. So I would like you to kind of look at this picture and look at the car park, that why Isambard is being built like that. And the other thing is they are also a digital first facility, so they are going to be the user of Isambard. So this is the 5,200 GPUs in 12 Cray EX cabinets, and it's in a factory in Chippewa Falls. It's being built already. So just look at it, 12 cabinets. Because one of the questions I still get asked, why didn't you get, if you have to build an AI system, why didn't you get an NVIDIA DGX box or a SuperPod or something like that? So we said, and we wanted more GPUs, and the space was limited, as you could see there. So we did some very simple calculations, and we said, if we have to fit that many GPUs in DGX boxes, we would be needing a lot more cabinets. And we will not only be taking the car park, we will be probably taking part of the motorway, or which is called freeway here, and more. So that was a no-go there. And here is where I have my simple comparison is why we chose what we chose in terms of architecting and designing the system as compared to DGX, like a SuperPod type of solution. And the disclaimer I have down there, majority of this data, because I think the business values for some of these things could be slightly different. So I used this information based on publicly available, and then I asked ChatGPT how much a DGX SuperPod costs. So these can be disputed, but it cannot be completely foreign. So Isambard-AI, in terms of space, I think I made this case already. We just didn't have a space, so it had to be in that format. You didn't not more compute. In terms of power, again, this is an estimate. So we have an estimate. We have an upper bound. Including everything, power management, storage, everything is about 5 megawatt. It has to fit in the power budget there. And we did like some really basic calculation and not including everything. We said it will be probably going order of 3. The total cost of ownership, TCO, for CapEx, that includes even the modular data center and everything, storage, and over 5 years is about 300 million pounds. And we computed even the lowest part of DGX type of style, we say CapEx, minus the modular data center, minus everything. We are still talking like factor 2 to 3. The huge advantage that NVIDIA software stack offers, of course, doesn't come as a built-in because it's largely a supercomputing technology. This is the problem of copy-paste. The slide I was going to show it is not next one, but I promise it will come later. So the software stack we are building on Isambard-AI is one of the innovative part, which I will show in a bit later. So which converges AI and computing software stack. And of course, if you use NVIDIA DGX and DGX SuperPOD, it's built in for that. So they have a huge advantage there. So the next slide is not the next slide, it will come a little later. I talked about some of these things, so I will come energy efficient compute, energy efficient data center. The node itself, and this is what we are getting from early user feedback, they are so happy. Of course, they would be happier if there were 8 GPUs and a lot more memory because they can fit a lot more model. But they are already quite happy that they can get very powerful GPUs and close to 1 terabyte of single address space memory. So this system is already proven for the UK users, a very, very powerful system to do both AI training and inference. And in terms of first, of course, this is, as I said, very fast moving project, but with HPE, Isambard-AI ended up doing the first things very first time. So the idea is if you have some support from your government to try doing something, and they trust you, they give you confidence, and they give you money, very important part, you can do a lot of things. So this is the first time one of the air-cooled data center put both air and liquid-cooled compute. It's the first deployment and power-up that was HPE told us was in less than 2 weeks. They usually take like almost 2 to 3 months for that, so it could be done, and we showed it could be done. And then it's combining, both the, there is a Grace and a Grace Hopper system, and you can see different parts there. And you can see my photo in the hard hat. So a few weeks ago, or maybe 2 weeks ago, I was thinking of converting these temperatures to Fahrenheit, but I didn't. And I said, we have an international audience, so I think I'm going to be okay. So in Bristol, it doesn't get very hot, but it does get hot. So, and the system is designed, again, it's not just because of temperature, there is a lot of condition, but around 27% with some humidity and other thing, the chillers will kick in. Otherwise, the system will work without, chillers. And we have this data center inventory manager, not only plugged into the compute, but also plugged fully into the modular data center and chillers and pump skids and everything. And when the temperature went up, we were able to even monitor how some of the chillers started working. So we will gather more telemetry data out of the system over time. So I think this community probably doesn't know that much. So there is a Cray user group conference that's going on for many decades. And so we wrote this paper about how we procured. And if you want a copy, I can share a copy with you. And it will be like a journal publication at some point. It pretty much talks about the procurement and build of Isambard-AI, but people really liked it so much, and and the paper didn't have any results at that time because we were just building it up earlier this year, and they gave us this thing. And this is the software stack, what I was talking about, and that makes everyone very excited. So if you remember, I showed you DGX and this comparison. How much time do I have, DK? Yes. Okay. This is the environment we are building, and I think this is the environment we can even work as a community to. And I think DK also talked about it's AI, it's MPI, but the software stack that goes around it. Because majority of the AI and machine learning users, they come from a public cloud environment, and they are, how do I say, they are familiar with a different way of using the system that our classic HPC users are. And things that matter to us a lot, I'm a very classic traditional HPC user person, they do not matter that much. It's the interactivity, it's the ease of access, it's the ability to grab a container and run it quickly. And elasticity, these things are very important. So talking to the users and with our understanding of the system, we said we have this like 6 level of a stack that we are working on. And it's working. Of course, it needs still a lot more work. So the first important is the native environment for AI application and frameworks. And there we are talking about ML flows, there are talking about some of the more user-specific environment. But by and large, they work on just grabbing an NVIDIA container. And we have now evidence to show how it is done. If someone builds natively, they just like bring a Conda type of environment and just do it. So it's largely Python-based. If it's not container, it's largely Python. And our HPC community, I mean, we just typically do not talk about these things. And then most of the time, they want to build and bring their own environment. From that part, in terms of interfaces, we see sort of 2 distinct possibilities. One is like the notebooks and dashboards. I think you probably all know that. And another one is what we understand, I think, the Slurm environment or command line. And also something that Ohio State University has been really leading, which is the open on-demand type of interface towards that thing. After that, things started getting really very, very different. And if you do it on the same environment, it gets quite tricky. But I think that's why we do think if everything was solved, that's what I told my team, if everything was told, the life will be so boring. So we have the Jupyter hubs, the Kubeflow. So Jupyter hub is already working. I will show you in a minute. And they largely work on the resource management and allocation of a Kubernetes style, service style thing. On the other hand, when we have fixed size jobs, we tend to have like a Slurm shell type environment. And we have both kind of working on our thing. Majority of this in the public cloud work on a multi-tenant environment, and the infrastructure we have chosen, it supports that. I was hoping to talk a little bit more about it, but I will just summarize it like very quickly. When I started, looking at it, what AI is doing for science, I was so surprised and shocked. I said, I must be living under a rock that I didn't know that AI for science is such a big thing. And this is a paper, it's like more like a survey written for Nature, and you can look up. It talks about scientific discovery in the age of artificial intelligence, and it was published last year. And it really looks at how AI moved from really almost as a branch of science that is impacting all the complete life cycle of science, from hypothesis observation. It's a very dense paper, and it goes through different examples. And then there is still a lot to do, because the accuracy and the fidelity of the work you do depends on right size, and then depends on the scientific intuition. So some of the examples I copy that are more sort of easy to grasp, because the paper is very dense. I feel like I read it 2-3 times, but probably I got 20 or 25% of it, even less. And then they talk about really training someone to pass the US this US medical exam, and they say MedQA is the one they used. And they say that when they trained the model on a certain data set with a certain thing, it passed up a certain threshold, but not like in less than a year, the model was really outperforming the human physicians. And it's more than, I have never taken, I'm not a medical doctor, but it's more than QA or simple text analysis. And this is the picture, I think NVIDIA also should. It really kind of conceptualizes the relationship of the parameters and then what you can do with it, I think, in my very layman terms that I can sort of describe. And there is a lot more detail to these things. So the larger parameters mean you have a higher degree of ability to reason and, from language understanding, physics QA, you can get into our dialogue in some sense. But higher parameters also mean that as they are increasing, both in open source and closed source environment, you need more compute. So when we were talking to our early AI users, they wanted to know how much performance we are getting in there. So we used like a very powerful laptop, because that's for the most part people will use. And we say, if you go to Isambard-AI, what would you use? So you can see the specs. So on the normal laptop, you can do 466 AI, trillion operations per second. And we said, as you go to the more model, and going back to, looping back to the AI for science question, you can do higher parameter models going to the bigger system. And again, these are like estimates in this thing. So I said 10.4 million AI trillion operations per second. So early users results and next step. So this is like a word cloud. So what we are doing right now, I started almost 2 months ago in the AI phase 1 system, which is 168 GPUs. We started what we call them technical readiness projects, where people fill out a form and then they start using the thing. So this is like a word cloud from the phase 1 platform. And now coming back to what people are already in the first few months using AI phase 1 system for. So these are coming again from the form they fill out. So the people are doing Gen AI work, and these were about 20 to 25 forms. At that time, we took this data from. There are some large language model research as well. Some have a combination, in fact. There is image and video-based research, and then there are these deep neural networks. And what I said earlier, we asked them to identify how they will use the machine. And we had few choices, and like some were other. But the thing that has really stood out to us, that people are going to use or are using a lot of PyTorch. Again, this is no revolution to the community. The thing to think about for PyTorch, and this is what I see, the tension between. So we hired some people who are coming from the AI community in the team, and we hired people, who are coming from traditional HPC community in the team. When people saw that, some people said, okay, now we need to optimize and tune PyTorch to death on Isambard-AI. That's the way to go, because people are using it. But that's not how and the AI team members, they say, we need to make sure the container from NVIDIA work the fastest on our environment. The reason being that the container optimization coming from NVIDIA is optimized, of course, for a different network and environment. But sometimes, or more than sometimes probably, NVIDIA doesn't upstream the changes and tuning. They do even for Grace GPUs. So there are results, not from us, but also from my other data center, CSCS, showing even if you tune and optimize PyTorch, somehow the NVIDIA container works still the fastest. This is amazing. So we really need to treat containers as a first-class citizen on these machines. And we are, as I said, gradually involving this cloud and HPC convergence software stack on the machine. As I promised, there are results, and DK told me his team will show his results from Isambard-AI. But in this case, I didn't use MVAPIT as the MVPI library. I used Ohio State benchmarks and some of the team members. So these results are collected by me and others. So Cray MPI. One of the things we are working with both HPE and NVIDIA is the current version of the kernel that is on the HPE system based on SUSE Linux is about 5.14. NVIDIA, if you look at the Grace, because it's such a new processor, ARM processor, they recommend version like 6.9 or something. So there is a huge mismatch of the kernel versions on the machines, which is a challenge for us right now, but also an opportunity for us to move to higher kernel with HPE support. We just can't put our own OS on this machine because we get from HPE many drivers such as Slingshot drivers, such as Lustre driver, etc. So this is still ongoing work. So these are by far not the final numbers. I was quite surprised because I was used to using Slingshot in my other places that the grace-to-grace internode latency was quite high. And we are looking into it. I think there are some, again, it's such a new processor, but we need to understand it's because of the old kernel, it's because of some other things. And it's about 1.2, 1.3 lower than what I can measure from a x86 processor on both ends. With GDR, you typically add 1 microsecond on top, one hopper, Rosetta switch. Bandwidth is pretty much not affected. So we are really getting close to peak bandwidth with the MPI bandwidth test from Ohio State. Around 24 is 100. The injection is 100 gigabits per second. There are 4 cards per node, and GDR numbers are quite reproducible. And we also did 4 NICs per node test, and the results pretty much tally. So this system, for low latency, it needs quite a bit of improvement. For high bandwidth, for GDR, the system is neatly set up to, for instance, if I say, look at PyTorch, the system is running PyTorch with multiple GPU and multiple NICs without a problem for the users. So this is my last slide, or second to the last slide. So what's happening now? What has happened so far? I talked about a lot of things, and what's coming next. We have a very small, what we call phase 1 system with 168 GPUs. In fact, 2 nodes are converted into external login nodes. This system is so busy right now. People are very excited, and we are still trying to learn and tune it. So it has been up and running and available almost from May to the users, May, June. But when people talk about Isambard-AI, they are expecting 5,000 plus GPUs, and they go on this machine and they say, where are all the GPUs? I say, we do not have even a data center and power to bring all these things up. So we were initially expecting the system will show up in September. Now we have some site and other delays, so it's moved a couple of months. But hopefully in autumn, we are expecting the delivery of the new modular data center and the scaled out system, because system is built. We showed it in the factory. And that system will have not only more flash-based cluster storage, but it will also have AI optimized vast storage where we could plug in and do additional data. And with that, I will finish. And I like putting this thing out there. This came out from the AI Safety Summit now it's a year, and time goes by fast. And it's for me as personal target and ambition that AI is really genuinely going to support the mission of AI safety research, because we as a society need that. Thanks.
So let's first thank Sadaf. Well, we have time for a few questions. Yes.
So the modular data centers, you kind of describe them as Lego blocks. Is there a plan to start stacking them on top of each other, or are you just going to go out further in the parking lots?
Yeah. So as you said, these are Lego blocks, and but these Lego blocks are built by different companies. So we are getting ours from HPE, that is subcontracting with this company in Netherlands. I think they subcontract with a different, supplier in the US. But other OEMs like Dell, Atos, and others, they all provide it. So we are building out because we looked at stacking up, but stacking up for the reasons of planning permission and other thing turned out to be riskier or more something that HPE supplier didn't support. But I at least know one institution, SEA, which is the French nuclear agency, they are building a stacked version that you normally see a data center from a resource plane and a distribution plane and an IT plane, a machine room plane. You can do that as well, and these are being done. So if you're interested in that one, you can definitely check out, say, a solution in there. We didn't do it. I mean, I do not have a background, so I don't know at what point what was the deal breaker, not stacking up. But from what my understanding is, it had to do something with planning permission and risks to the facility. But there is no reason it can't be done because it's already been done in a stacked manner.
Any other questions? Yes.
Thanks for presentation, and it is honestly, so I don't pretend that I understand how you really make this thing work, but by looking at the numbers, it is quite impressive that your sort of power efficiency is a lot better than NVIDIA's, while you're using the parts from the NVIDIA. Right?
Oh, that's probably
right
quite
now,
easy.
I have I have a few questions on that angle as well. But right now, let me ask another question from a slightly different angle, because one of your focus is on the CUE, the carbon usage effectiveness, while you are still consuming 5 to 10 megawatts, depending on how you look at it. So maybe I missed that part of the presentation, but I assume that you rely more on the nuclear power then, or what other natural type of power resource you are using? If not, then I assume that it's a nuclear power. Then the nuclear power has sort of another side effect in terms of the ecosystem, right? So I'm wondering whether you have a sort of a roadmap to move on to more natural power sources, or it just keep using the nuclear power is the answer for CUE, regarding the CUE?
Yeah, I think that is really a very interesting question. So I will try to give like a very simple answer, because the answer is not simple, because if the answer was simple, we would all be doing it. We wouldn't be talking about it. So one of the very simplest thing to do is to say that how we can show the government, when government gives you money, you are saving money for them. So if I say I'm not doing more carbon generation, but I'm paying more power bill, the government won't be very happy. You see what I mean? So it's a combination of reducing the operational power bills at the same time, while making sure the sources of power are also that. So to answer that question, so if I can just like hypothesize, even if somehow a very efficient nuclear power plant is available, I would still not build a system that consumes more power to run for the things that it offers, because ultimately it would mean the power bills are higher. Right. So that is the calculation, the very simple calculation. But as you know, these things are more complicated when you sit down and do these things, because
Yeah,
Yeah, the project is not big enough to change the energy grid of the United Kingdom easily. Why we are more efficient is your other question. If we are using NVIDIA technology, you are absolutely correct. The power needed to run a super chip, Grace Hopper super chip, is no different because it's a Grace Hopper super chip. Yeah. But if you look at it, that how a blade is designed, how our DLX blade, a DGX blade is designed, is already quite different. So how you power up an 8 air-cooled dense, or air to liquid cooled dense GPU system versus these tightly integrated design system, you can already start seeing these efficiency gains creeping up, blade by blade, cabinet by cabinet, system by system level. I haven't done that breakdown I have done a system level breakdown, the one I showed you, from a DGX SuperPod to a EX cabinet. What may be something good to look at it together, if I take even an HPE 8 GPU, very normal AI box, and a HPE EX, very dense blade, how much is that difference? Is it 50%? Is it 2x? To power up a super chip sitting in that form factor versus the other form factor. I haven't done that part, but maybe to look at. I don't want to make a guess, but I think then the efficiency at a system level is a combination of all the efficiencies that start stacking up. But you are correct. The other thing I will tell you is that because the system is so dense, I didn't talk about it in here. Each super chip can go like 700 watt, this Grace Hopper, maybe a bit higher. But because things are designed in such dense thing, the HPE has to cap it around 600 watt. We can't go higher, otherwise, bad things will happen. So you also then, by some of these design, you bring other constraints to the machine, which may or may not be something you would like. And so that's why the number one system on Green 500 is another Grace Hopper system, but designed very small in a different way. So there are these decisions you do because of a scale, because of other constraints, which we have taken here, as sort of I mentioned. But I haven't done systematic study on the single node and how these efficiencies start creeping up, which would be an interesting thing to do.
Okay. Thank you.
Okay, so I think with this, I think Sadaf will be here throughout today, so please feel free to interact with him. So let's give a big
Thank you.